right, I'm gonna do a short stream again. I have been learning a little bit while I did not stream. It was off stream about scikit implementation of classification and regression trees, which, as a reminder, is a way to solve, well, classification and regression problems in machine learning. But for now, we're just focused on the classifier part of it. So if you have a bunch of data, training data, so to speak, for example, like the iris data set, where you have like, this is the length of the flower, this is how many petals it has, and then this is the type of iris that it is. And you have a bunch of data entries like that. You can teach a decision tree to then predict for new inputs what type of iris flower it's going to be. That's kind of the base idea of what these things do. And then there's gradient boosting and extreme gradient boosting that builds on top of decision trees. So that's what we're building. I'm going to implement it in C++. And I went through the scikit learn code for all of this stuff. Just learning about how scikit does it. And I feel like I'm ready to start writing at least something. I don't think I'm going to get very far right now. I'm just going to probably do like an hour session, something like that. But maybe we can at least, you know, get started, run into some errors, fix some errors. We'll see where we get. Right. Also, another thing about scikit is that it supports a lot of features. So I do not need to write all of the things that scikit has. For example, for a criterion, they support Gini, entropy, and log loss, which is how you measure impurity, blah, blah, blah. We'll get to that point. But I don't need 3 of them. I'm just going to use Gini all the time. So that's already going to help. Also, they support stuff like monotonicity, which I don't think I'm going to implement for now because I simply don't need it. So I'm going to be like, I will implement things like monotonicity and other features like min samples leaf, min weight fraction leaf, and all of that once I get to the point that I need all of those features in my decision trees. I just simply do not need them right now. And I have to be a bit careful with sound so that it's not too loud when I type. That's kind of hard to check. I'm just gonna hope for the best that it's not too loud. Okay. Right, so I was writing a header file for a tree, and then we gotta implement a decision tree classifier. Now, where do I even get started? I'm gonna have to plan. How do I get started? So I'm gonna need to build a decision tree. So basically I need a tree, and in that tree I'm gonna have nodes. It's gonna be a binary tree, and then each node is going to contain sample data, sample training data. Now, what's the best way to store that? Let's think about this. I don't want to just do I'm gonna like think about it on my own, and then once I think of something, I'm gonna check the scikit-learn implementation just to like verify whether I thought correctly. So, okay, let's think about this. We have the fit method, and we want to start building a tree. So maybe I can start by just writing code that randomly creates a tree which has like some of the data inside. So it can have like some random data in each node, and I can check whether that works. That's like a hello world of this, and at least it's useful. Then on top of that, I can build the algorithm that correctly splits the data, but I can do that later. So that's a good starting point. Let's start by just making it possible to make a tree. Oh, don't tell me. Really? Oh. My keyboard died. That's epic. Hello? Alright, now it's good. Let's start by just making it possible to make a tree with random data inside. Doesn't really matter. So we might have to implement here like a way to add a node to the left, to the right, whatever. And then once we have that, what do we do? So we're gonna have to implement the splitting algorithm, which basically means go through all of the sample data, go through all of the training data, and then check. At first I'm gonna implement the best split because there's a best split and a random split. So I'm gonna start by implementing the best split. So that means go through each feature, and then I have to check the threshold, and then there's a criterion that's gonna get involved. That's a lot of stuff all at once. But I guess I can define it just like start writing the training algorithm. And maybe data structures, right? Because I'm gonna need a way to organize all of this. So that's gonna be go through all training data correctly, because I also have to implement a correct way to go through it. It involves some random reordering, and then for each split candidate split position, calculate how good a split would be, Gini impurity, something like that. Yeah, something like that could work. Gini impurity. That's too abstract, but I'll see about it when I get there. Right. So let's go and make a file called tree.cpp. And this has to be HPP. And here we're gonna implement, well, we're gonna work inside of namespace gboost, and we're gonna implement decision tree classifier fit, and that's void. Let's just copy pasta this. So this, and this has to be wait, how do you write this in C++ again? Like this? Right, and then we do this. Okay. All right. So X here is going to be the input data, and Y is going to be the, so X is like the features and Y is the values for those features. I think it's fine to have it like this. Theoretically, I could also have it, I could have it all as 1. Wait, this doesn't make sense. No, it does make sense. No, it doesn't make sense. Input is a 2-dimensional array. Yeah, it's a 2-dimensional array. Yeah, like this. So we're gonna go here, and then two-dimensional array of doubles. I think that's gonna work fine. Because it's basically a table, right? Okay. Now let's say that we just want to make like an empty tree that has a left child and a right child. And I'm using this tree array structure. Usually you don't make a tree like this. You make it like, I guess a good way to make a tree is a struct, and then you can just make a node. And then you can have like a pointer node to the left and a pointer node to the right. And, you know, you can have some data. But this is not efficient, because it uses non-contiguous memory, and then the computer needs a lot of time. Well, not a lot of time, but a significantly bigger amount of time to access the data that is left to right, because the data is not like grouped next to each other, or at least it's not guaranteed. I'm sure that the computer tries to optimize it so that it is grouped together, but there's no guarantees, and then the CPU can't use its cache and all that stuff. So that's why we use a tree array. And the way a tree array is gonna work is that these data points are gonna represent everything. This doesn't make sense. This should be a vector of integers, and we can call it IDs. Yep. Now, it's okay, it's just a few types. I was thinking about making like an alias for this type so I can easily change it, but that's not necessary yet. Okay. So let's say I initialize a tree array. So basically I just want to make a tree right now. So let's just say I do tree array T. Okay. And that's my tree. Now, how would you add the root node to this tree? Did I implement this tree array correctly? All right, let's see. Basically, I want t.left. If I do t.left 3, then that means for the node with id equals 3, get the left child. Get the id of the left child. Does that make sense? I think that makes sense. How does 3? Wait, what? Really? Okay, site 3. They use nodes. Okay, let's see how they did it. Oh, they use a pointer. That is weird. No, int pt. Isn't this like a pointer to an... That doesn't make sense. Why would this be a pointer to an integer? Okay. Oh, they have array of nodes. And that is a pointer. And all of this stuff number of features, but this is just like properties of the tree. And then they have nodes, and nodes are made left child, right child. Impurity, that's all of the data that feature used for splitting the node. Threshold value at the node. Okay. I'm not sure that this is this the best way to do this? Okay, let's look up documentation. Example C++ implementation of a tree data structure implemented as an array to be compact and contiguous in memory. It's GPT-5 mini, but there should be examples of this on the internet, so I'm just looking for a reference. Array 3 sounds like a better name than the one that I'm using, but tree array. Yeah, array 3 is better. And then we're going to go to tree.hpp and then name this to what's the, oh, it's empty. Whoa. Okay, whatever. Array 3. Index means null. IDXT, what is that? Whoa. Oh, they did make a type alias. Okay. Add root. Okay. It only contains IDXT. Add child. Allocate node. Okay. Operator overloading. Parent off. Children off. Yo, this is way too overkill. Okay. Okay, first child. What is first child? Allocate node. First child dot push back and pause. Next sibling. Okay. First child and next sibling. Yeah, but this is using. Okay, this is more of a generic tree apparently. First or most recent child. That doesn't make sense. First child can't be most recent, but I guess I'm missing something. Okay. Values. First child, push back and pause. What is npos? Static constant expression and pause equals -1. So that's like null. Insert at front of parents child list. A next sibling. So it takes size of values. Converts it to an ID. Yo. And then it uses next sibling at that ID and sets it to first child par. What the heck? I do not understand this. Okay. Let's increase this window size because I don't understand what's going here. What's happening here? So type name T, this is not valid because you didn't even restrict this so that it has a size property. Wait, did you? So allocate node. You're just using a reference. Oh, it's using values.size. That's not the val. That's over here. It's over here. Okay. Yeah. So basically, this is just. Whoops. Oh, that's probably very loud. My microphone dropped. Okay. So basically, that's just like the next entry of values. And that's the ID. Okay. And then into the values, it pushes back this thing. So it adds things into values. And then it adds parent. Okay, parent that push back. That doesn't, okay. So you set a value and you set a parent. That's how you add a node. So you specify what value you want. Oh my gosh, this microphone, dude. I gotta get a stand. Okay, so you specify the parent, the ID of the parent, and the value. That's how you add a node. And you're storing first child next sibling. And so if you were to do, right, so in order to get the value, you entry into this values array with the index that you get from allocate node. And that's also, I guess, what the overload operator does. Yes, it is. Okay. Yeah, right. So yeah, we're not going to be deleting nodes, so that's fine. Okay, so if we go back to my tree. What? Array tree. There we go. Yeah, we don't store IDs at all. We just have left, right. So this is where we're gonna store IDs. Okay, so I need to implement a way to add features. So the way that would work would be, okay, I can see how that would be useful. this just to be nice, so that I know that this is an ID for readability. And one thing I'm gonna need is a method to add a node. So that will be IDT add node, and do I need to specify whether it's left or right? I'm thinking about how the training process is going to work. I kind of just want to add a node and then be able to modify the data afterwards. So theoretically, maybe I don't even need to pass any parameters to add node. For now, I'm just gonna stupidly pass is left. Does C++ support default values? It does. It's been a while since I coded in C++. Now, this doesn't quite make sense because I don't know which. Yeah, because I'm gonna have a lot of leaves when I'm adding a node. So I don't know to which leaf I am adding a node. So I'm also gonna need ID. And then okay, and then I'm gonna make an ID for the new node. This naming is terrible, but the ID for the new node is gonna be, so I'm gonna cast to, well, there's no need to write it so verbosely, right? The ID for the new node is gonna be left dot size. If is left, then this is gonna be the new node ID. But if it's right, then it's gonna be different, which means I'm gonna need to initialize it here. And then here, we're just gonna do like this. And then else, we're gonna have the same thing, but we're just gonna do right.size. Okay. And then we're gonna return new node ID. All right. Now, I'm also gonna need to track parents, right? So I'm gonna have an entry parent. Yeah. This one did it the same way, right? You track parents. Yes. And then if you want to get a parent, yeah, you have parent of, which just returns parent of I. And how do you get children? Yeah, you track all of that in arrays. Is all of this worth it? What if I was to... Yeah, but see, the problem is, what if I had pointers? Like, what if I had nodes and then pointers to other nodes? Each node would have to contain... Each node would contain some features. Now, how would a node contain features? Because that's what a decision tree does, basically. Splitting the data means that at each node, we are splitting the training data and sorting it as well. Which means that each node is holding some training data. Now, okay, so each node is holding some training data. How would that work in memory? Because we have sample data and then we do a bunch of reordering. Wouldn't that simply be... Isn't the only thing that we need, like we're gonna have in memory a features array. And then each node, the way you know which data it has, you can simply know that by knowing where the start position is and where the end position is. So that's two numbers. Yeah, you need the start position and the end position. And that's all the data that needs to be contained inside of a node. So this doesn't quite make sense. I think I'm gonna implement this as a pointer because, I mean, I get how this data structure would work, but I don't see how this would be a benefit unless I need to hold this features array, but I don't. I don't need to have this features thing with a bunch of data. That's if I have... Okay, but I'm gonna have other... Okay, let's see. How do they do it? So they have left child, right child, feature, threshold, impurity. Yeah, it's just a few numbers. Well, it's not a few, it's... Okay. And then they have array of nodes. Right, and then node 0 can be array of values. Then they simply have left child and right child. Oh my gosh, which one is better? Feature. Okay. Okay, the thing that is confusing me a little bit is this features thing. Because I'm not going... No, this is wrong. So I'm not going to hold features inside of the tree. No. No. What I am going to hold inside of the tree, I'm not sure, but let's just pick something that I'm going to hold. I'm definitely going to do this. Feature used for splitting the node. And that's just an integer. So int, I'm going to have the same thing, and it's going to be called a feature. And this is going to be feature used for splitting the node. Same as in scikit-learn, exactly the same. And if I'm going to go for an array tree implementation, then this needs to be a vector, because each entry represents one node. And okay, and I'm only going to need left and right. However, I can make this, I can use the LLM suggestion, because LLMs is more generic. It's not a binary tree. The tree can have any number of children, 3, 4, 10. It doesn't matter. Kids. So this kind of implementation can have any amount of children. So I'm trying to understand this first child and next sibling, right? So, okay, so basically I have an ID of a node and I want to find its children. Now, a naive way to implement this that comes to my mind would be to simply have an array of its children, right? So that would be like a vector of vectors, and every time I index into the vector, I get the IDs of the children. A problem with removing left and right and going for this kind of implementation is that for me it matters which one is left and which one is right. So I want to have left and right. Yeah, but then it's easy, right? Because I would just pass in the parent ID, and that would be, that would be the left. And since this is the parent, yes, okay. No, so this is fine actually. I don't understand the suggestion that the LLM gave yet. I'm gonna understand it for funsies. But in my implementation, if I just go this is possibly not correct. Yeah, this code is possibly not correct. Because what I want to do is I want to say left and then ID equals new node ID, and right ID is nothing. So if is left, else yeah, so this is what we want. But how do I get the ID? How do I get the ID? Well, I could just maintain an ID counter and just keep incrementing it every time a node is added. That's one way to do it. I don't see how that would be a problem. But let's see what an LLM will come up with if I ask it to change this to a binary tree. Can you show what this would, can you show an example implementation of a tree for a binary tree? Let's see. Okay, so it's using data, and every time it adds something to data, it pushes back. So this sort of feature, okay, I see. I see. Well, that's not too bad. I like that. That's actually quite nice. Then later I can define what kind of data I want. So let's use that. And here we're gonna make private std vector data, what t, that's gonna hold data. All right. We're gonna hold data there, and then here we can just do data.size. We can delete this. Yeah, this looks good. This looks good. Now let's see if I missed something. Insert. Heap style. All right, best for complete or nearly complete binary trees. Children indices are very memory and cache friendly. Yes, but it's worrying a lot about, I guess it's worrying about things like finding the parent or so. Yeah, because this thing can find the parent automatically. But I can, you know, it's not that bad. I can just store parent information. But I'm not gonna need it. Then it has left and right. Yeah, but that's not necessary. And yes, this should be called a binary tree. Wait a minute. All right. Okay, so let's see. Values parent left, right. Yeah, this is just for finding the parent. I don't need this right now. I need left and right. So this is basically the same thing that I have. Okay. Yeah, but isn't root just gonna be the 0, 1? Yeah, root is just gonna be 0. Exactly. The first thing that you add is gonna be the root. So it's fine. Yeah, this adds left and right, left. Yeah, this is one thing that I'm not gonna, it doesn't seem like it, in add node, it doesn't seem like it cares Is it to the right or to the left? Because a binary tree... Yeah, I don't like this part of the implementation. Why? So you push back something to values. You push back to parent, that all makes sense. But then why do you push back and pause to left and right? Because left of index, yeah, okay, this is not gonna work. I'm like this is no good. Okay, see the downside of this. Okay. Okay, I see why you have to push back. Every time you add a node, yeah, how can I know that left ID is actually going to be a thing? I can't know. And the way this guy solves it is with set left and set right. So this adds a node to the tree, and then it sets left or right. Assert, yada, yada, yada. Okay, where does this assert that? Here. Left of p equals child. If child is not equal to end position. Left parent equals child. And then if child is not end pause, it also sets the parent. So it basically does the same thing I did. And over here, it simply pushes back because when you add a node, then you added a parent. So you just basically need, I get it. Okay, I get it. I get it. So we're also gonna do a left push back and pause, and right push back and pause. Okay. Yeah, so this one separates adding a node and setting it as left or right. Should I do that as well? Because adding a node, you kind of want to focus on adding the data. You do not want to bother with this left or right. You want to do that later. So I think the thing that the LLM suggested is better. Yep. The thing that the LLM suggested is better. Because you want to be able to add a node and then later wire it up. And this does a pushback of value, which is a copy. We can possibly optimize that with a move operation. Although we can do that later, because because this makes a copy of value, so we're copying every time. And this is const, but then here it's no longer const because we already copied it. Okay. But I'm basically gonna do it the same way as here, because that makes more sense. So let's delete these parameters, and we're gonna do const t value. Why does it even use parent here? Oh, to set the parent. Right, I'm not tracking parents for now, so I'm not gonna do that. And we can rename this to ID. Okay. Here we can data, push back the value, makes a copy of value, possibly something to optimize, and then here we're going to return ID. This is good for adding a node, and then later we can wire up the node. So we can do, let's just do it the same way. We're going to have parent ID, and we're going to have child ID, and then we basically just set left of parent ID is child ID, and then we're going to do the same for set right, parent ID, child ID, and we're going to say right of parent ID is child ID. No node. Okay then. And I believe this should work fine. Then we can do a cheeky we could test whether this works, but I kind of just trust that it works, so and testing it is a bit annoying, so I'm not going to test it right now. I think this works fine. We don't need this. We can remove that. And then we have a basic binary tree. Now another thing that we're going to need, since we did it this way, is we're going to need the data that we're storing inside of a node. And one thing I don't quite know is, since we're storing certain samples at every data node, how am I going to actually do that? How am I going to represent that? So those are some questions to answer. I have to store samples at each node. How do I do that exactly? So that's one question to answer. And then another question to answer, or actually thing to do, is to implement the data that will be stored at each node. This is kind of a sub question, but it doesn't matter. And I think I'm going to define it over here, and I'm just going to call it, we can call it decision tree data. good name? Decision tree data? No, because we're storing it at the node. Let's just call it node data for now, which is generic. But this library is gboost, so I don't need to be like extremely generic. It's fine. I'm not going to have other types of nodes here, at least not for now. And then later, if I do, I can rename it. So for now, I'm just going to store like an integer, and I'm going to call it feature. ID. Well, now I see that this would actually be useful in other places. So we can do here. Oh, we cannot do that there. Can we do it here? Yeah. Okay. And then we can do this IDT ID, or actually index. Well, now I see that this doesn't actually make sense. So let's just do int. It's not an ID. Index of the feature. Index of the feature that the node is that we're splitting the data on. That's it for now. And now I have to answer the question that I asked, which is, how do I store samples? How do I store samples? Well, let's see how does scikit do it. Threshold impurity, it stores the number of samples and it makes no mention of absolutely anything else. Yo. Well, it says the number of samples. Maybe that's enough. Maybe that's enough information. And then maybe from this, it deduces. Yeah, that's probably how it works, right? If we go into the splitter, and then we search for, well, where do we search? Let's do it here in node samples. No, 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 no. Wait, what is weight of samples? Yeah, it's just 4 mentions. Criterion weighted node samples. Right, so it has this sample, it has these samples held externally. It has this split record. What does it do with the split record? Init split. Then it has current split. So it initializes new split records, has the best split and the current split. Right, so this happens for every node. I'm gonna have to do it like this. So is defined in okay, let's see, what data does that hold? Split record holds which feature to split on and which position we split on. Threshold improvement, impurity of the left split and the right split, and other stuff. Okay. But how do you know for a given node which data it has? Because, you know, it starts at the root node. And then what? So it starts at the root node. And then how does it know what data is to the left and what data is to the right? Well, if it knows the position of the split with the split record, then it can use that to deduce what is in the left node and what is in the right node. So in the node, you don't need to store any data within the tree itself. But you need to then store these split records. And if I remember correctly, this method at the end returns split 0 equals best split. Wait. Yeah, so this is wait a minute. Yeah, so this loop determines the best split, and then when the loop finishes, this does something for missing values. We're not interested. And this is if we're not done, I guess. Yeah, if we're not done, then we do partition samples final, which basically just reorders sample data. Criterion updates. Set some values. This does some copies for copying for constant features. And then we set split 0 equals best split. And we always do split 0. But bro, what does split 0 actually mean? Oh, hold up. Because this is receiving a pointer to a split. So split, so this can be considered an array of split records. So that, right? Yeah, right. Because then split 0 is actually the first entry of the array. Fine. But then what happens with others? So we have to find who the heck calls this. Yeah, node split. Okay. And this thing is already provided with the split record. So I guess that's called from 3, not pxd, 3 pyx. So we need to see pyx. Node split, split node actually. Bro, split node. Bro, what's the hell is wrong with me? Splitter. Yeah, it's node split. Isn't that here? Yeah, it is. What is wrong with me? Okay. Depth first tree builder. Wait, which tree builder am I using? I freaking forget. Yeah, depth first tree builder. There's best first tree builder and depth first tree builder. I'm gonna go into best first tree builder. Best first tree builder. Yes. And do you have node split? Is this part of my class? Yes. Yeah, okay. And this creates a split record split. Wait. This defines a split record, which is not an array. It's not even a pointer. Okay, so I guess the 0 thing is just a way to dereference in Cython. So it's not an array. It's just a way to dereference. Okay. But this is called add split node. So it creates a split. Adds node with partition start end to the frontier. What is a frontier? What is a frontier? That is line 577. Frontier record. Let's see. So it does the node split, modifies the split, and then what happens with it? Okay, then this frontier record gets data populated apparently. Yeah, so whatever you do, the frontier record has its data populated. So is the frontier record the thing that's ultimately used in order to determine what data goes inside of each node? So ultimately, is the frontier record what determines what data goes inside of each node? Question mark. Let's see. Frontier, okay. Frontier record. Record of information of a node, the frontier for a split. Those records are maintained in a heap to access the node with the best improvement in impurity, allowing growing trees greedily on this improvement. Yeah, so it holds a node ID, start and position depth. Okay. We found the answer. Yes, it is. Whoops. We found the answer. Yes, it is. The frontier record is what holds the data for each node. Which is interesting, seems a bit redundant, but okay. I feel like given the way I made my tree data structure, I don't need this frontier record. I feel like this is a mistake in scikit-learn to have this frontier record. Unless I'm missing something, which I probably am, because they would fix it if it was bad. But I don't see why I wouldn't simply have it here, right? Why wouldn't I just have it here? Then here I can do start, end. Why do you have position start end? Because this is where the split happened for the left and right, I guess. This is the, so start and end denotes the data that the node contains. And position, I guess, denotes where it was split. I don't know if that is so relevant. I guess it is at some point. I can add it later. So far, I don't see its purpose. So, start index of samples. Samples start index. Samples end index. Start and end. Describe the samples that the node contains. Indices of samples. Indices of samples. So we're going to actually delete this because I want to describe something. It's like this, start, end. This means that start is included, end is not included. And I think the convention is to use this bracket. So start is included, end is not included. Is that gonna fuck all my brackets now? No. No, it works fine. Okay. All right. Yeah, one thing we're definitely gonna need is also double impurity, since we're already here. Improvement, lower bound, upper bound, middle value. I don't know if we're gonna need all of those. The thing is though, there might be quite a few things that we don't need, because scikit-learn has some features that I'm not gonna implement, at least not yet. Is leaf. Okay, we'll see. Maybe I'll add is leaf. Actually, that's probably quite, that sounds quite useful. Is leaf. Yeah, okay, so that data seems legit to me. Okay. Now, how are these samples going to work? So we're going to have these samples somewhere. That's probably the next thing to focus on. Let's start working on samples. Let's start working on samples and also ensure that the indices in node data can refer to samples correctly. Okay, so the way that scikit-learn does this, so we need to go to the algorithm, tree.cpp here, and this is going to be node data. There we go. So when it comes to the samples, the way that scikit-learn does this is that it makes an array of, right, so it makes an array called samples, and this is an integer array. So what it does is vector of integers, and it's called samples. And this is going to be indices referring to x. And then it can like rearrange this and so on and so forth. like this, I believe. No, wait, the first one is size. And the second one is the value. And then we're going to initialize it to indices. So we go for, now I want to do this, like I want to be fancy, for auto e of samples. And if I make this a reference, so let's not use auto here because it's confusing. Int reference e, I can make I equal to zero and then plus plus current. I can make this an integer. I think this is a way. Is there a cleaner way to do this? I mean, I could use yeah, in this case, this kind of array doesn't make sense. But I'm just kind of wondering if this works. Just kind of testing my C++ skills. And so let's test it out actually. So for auto I of samples, let's see if it modified the values. And we're gonna include IOStream so we can print values, and we're gonna do cout I and then end line, and we're gonna need, why does this say that this is not used? Oh, there we go. I just wonder if this works. So if we go into main, then we're gonna include 3.h, actually 3.hpp, and then we're gonna make a decision tree classifier. What is wrong? Oh, of course. Okay. So we'll make the classifier, and then we're gonna need some data. Let's call it that X. And let's make that, it doesn't matter, like this. One more time. And maybe one more time for good measure. And Y can be just a vector double. We'll just make it. Do I need to do 0.0? It doesn't look like I do. That's nice. Okay. It just knows. I mean, that's good. And then if I do classifier dot fit xy, that should work. Of course not. Fit is a private member. Really? 3.hpp fit. Oh yeah, it it's private by default. It's not private any longer. Hello? Is that gonna work now? Yes. Okay. Or did it not initialize yet? No, it definitely initialized because it sees that there's no unused. And then if we compile this, not this command, cmake, what's the command again? Yeah. So cmake build. Use parameter warnings, that's fine. Undefined reference to, oh, I think I forgot to add source 3.cpp. Well, then how is it possible that Clang is working fine? And use parameter y, that's fine, I don't care. Okay, that compiled. So if we now open the terminal, where is that located? Build gboost, yeah. So if we just go build gboost 012, yeah, that works. Okay, sweet. That works. So we can go to the next step. This is quite ugly, it's kind of hurting my eyes. But I'm not gonna rewrite it. I could ask AI to rewrite it, I'm not gonna do that. Okay. So now we have samples that refer to indices of X. And maybe now we can start to write training code. Okay. Where do we even get started? Right, where do I get started writing the training code? Okay, let's think back to how training works. We go through every single sample, and that's not correct because we don't go through every single sample. We don't go through every single sample. We kind of loop through the samples. We do not go through every single sample, but instead we get those samples in a randomized sort of way that conforms to certain things. Should we get started with that, or should we write the code for the criterion? I kind of don't want to write code for the criterion, because that's something we're going to need only down the line. For now, I just need to be able to actually, let's go through the samples, and then for each sample we'll calculate, like we go try a split, and then we calculate impurity, we take care of constant features, we go through different features, and we find which feature is the best, at what threshold, at what position, for a best tree splitter, which is a lot of computation, but not an unacceptable amount of computation, I believe, right? Well, how much computation is that really? Let's say that you have 5 features, You have 5 features, so you have to test each one. And for each feature, you have to go through all of the data. And you have to do this at every depth of the tree. So it depends on the tree depth, which in turn depends on the number of splits that you're gonna have. But even so, it's like multiplication, right? So it's like number of features multiplied by number of training samples multiplied by roughly 3 depth. That's actually not so bad. Maybe you're gonna have performance issues like with very big numbers, but I don't have big numbers right now. I'm working on the Titanic dataset, and when you have big numbers, then the way to solve it is using random trees, which is what we're going to use anyway in gradient boosting. But for now, I just want to implement the best tree, not the random tree. Okay, I got sidetracked. What the heck was I thinking before this? Right, I was thinking about the next step, and I decided that the next step is going to be going through these samples. So best tree builder, where? Best first tree builder, yes. I want to see how Scikit does it, because they do a thingy that they actually mention when it comes to going through the samples. Wait, where does that happen? I might be thinking of the random tree. Okay, I got a bit lost. Let's go back. What's the entry point to the training process? So there's best first tree builder and depth first tree builder. Yeah, base decision tree, fit. Yeah, so base decision tree, that's a thing that's implemented in Python, right? Yes, that's implemented in Python. It has a fit method, and it calls best first tree builder or depth first tree builder. And what does it call? Let's see, classes. And let's see, base. Wait, what is it called? Base decision tree. And then there's fit method. Hello? Where is fit? Whoa. I wrote something incorrectly. Oh no, I didn't. It's here. Is this part of? Yes, it is. Okay. Sparse sort indices. Okay, that's just a lot of initialization in Python that they do. And then this happens. If max leaf nodes is less than 0. Yeah, so they almost always, yeah, they default to the depth first tree builder. I wonder why. I'm gonna have to look into the difference. I did not check the difference for now. But yeah, it says builder, and then it says build, and passes all of the data. And then if we go to the best first tree builder, I believe I marked it. Yes, and then there's the build method. Right, so this is the entry point. This is what we want. This method is called build, but it's actually fit. So the naming is not great. And then it has x, y, and then it initializes the splitter. Initialization. That's all fine. And then add split node. Add root to frontier, which is start equals 0, end equals blah blah blah. Is first is left. And then while not frontier.empty, pop head record equals frontier back, frontier.pop back, blah blah blah. Yeah, so this is what we're building, but yeah, this method in and of itself doesn't make it very clear where I should start. Wait, so where are we doing these splits? How do we get from here to splits? Yeah, this just adds the root node, which is fine. That's something we're going to have to do as well. And then while not frontier.empty, so it uses kind of like stack based, which makes sense. So it gets the root node, and then if the node is expandable, and then if we're not monotonic, okay, this is some value initialization depending on monotonicity. I don't care about that right now. And then it calls add split node, which is gonna make a left child or a right child, which will make the stack not empty, which will make this while loop continue. So that means add split node is the juice, right? Yeah, this is called. And what info does it get? It gets the splitter, tree, start, end. Okay. What I'm looking for is samples. How does best first builder or tree builder or whatever it is, how does best first builder start working on samples? How does it loop through the samples? Splitter node reset, impurity, node split. There it is. I know that this eventually leads to samples. So it calls splitter.nodeSplit, which eventually calls the function called nodeSplitBest. Okay. Yeah, so basically, initialize a stack, add root node onto the stack. For the root node, call the split method. That calls the splitter, and then splitter goes through the sample data. So what we're gonna do is basically we're gonna need the same thing, right? We're gonna need a stack of data to be processed, and then constantly keep pushing things onto the stack. And it's going to include start, end, and other stuff. Should we put that inside of node data? Yeah, I guess so. then how that connects back to the tree, that's a question, blah, blah, blah. Yeah. Okay, that's a thing for the next time. That's gonna be for the next time. Let's just write down where we stopped. Let's just write down where we stopped. Best first tree builder dot build calls add split node. Let's put this in quotes. It puts the root node onto the stack, well, the root node data onto the stack. While the stack is not empty, it keeps splitting. Every time it splits, it adds new nodes onto the stack. This process calls splitter. It calls splitter.nodeSplit, which is the juice. Next step for me is to implement the process I described above, and we go from there. Okay, that's it. We're gonna do that next time. I feel like from this point on, it's not too far to get to a working thing. I feel like in a week or so, I'm probably gonna have this down and implemented, which is quite awesome. And then we can use it to solve problems. Although the thing is, I'm also gonna have to implement gradient boosting, which is quite fun. Yeah, I feel like the decision tree thing, I can probably do it in 2 to 3 days. And then gradient boosting is, well, it shouldn't be that much effort on top, but I'm gonna have to implement random based splitting as opposed to best splitting. Yeah, we'll see. It's not trivial, but it's fun.